Welcome to The Explainer. So today we are unpacking a fascinating and honestly a pretty dangerous aspect of massive EPCI projects. We always tend to focus on the huge steel structures and those crazy heavy lifts, but as the source material shows us, that is almost never where the real danger lies. So let's just dive right into how tiny, seemingly insignificant connection points can literally derail billion-dollar mega projects. Okay, I want you to picture this. You've got two top-tier contractors, two cables, and exactly one dashed line on an engineering drawing. Out on site, two highly trained crews are standing on opposite sides of a physical gap, and they're stopped dead at that dashed line, simply because both of them assumed the other side owned the connection. Now, that junction box sitting right between them, it costs maybe $15,000, but the commissioning clock in the corner of the yard just froze. And every single day an offshore vessel sits idle, it burns through roughly $1 million. So that little $15,000 box, just because nobody actually owned the dash line, is now causing a massive delay that's going to cost millions. Crazy, right? To understand how something like that even happens, we got to get our terms straight. In the EPCI world, an interface, which you'll often hear called a battery limit, is basically any point where your scope of work, physically, electrically, or digitally, meets someone else's. An offshore platform or a huge processing facility, it's not just one giant monolithic system built by one group. Not at all. It's really this sprawling network of hundreds, sometimes even thousands, of glowing interface nodes where totally different contractors, different disciplines, and different technologies all crash into each other. Every single one of those nodes is a battery limit. And here's the kicker. Every single one is a potential failure point if you don't explicitly manage it. So here's the uncomfortable truth about all this. Projects almost never fail in the middle of a scope. I mean, think about it for a second. You're hiring competent, world-class companies, right? They do excellent, super precise work right up to the very edge of their contract. The piping is perfectly welded, the software is brilliantly coded, the steel is flawlessly cut. But the failure, it happens exactly at the edges, in those unowned spaces between the areas of excellence. They fail because contractor A did perfect work up to the line, and contractor B did perfect work up to their side of the line, but absolutely nobody on the organizational chart actually owned the line itself. The edges are exactly where your profit margin evaporates. Now, when we look at how this translates into technical reality, it's super easy to picture two massive pipes bolting together. But the battery limits that really require your intense personal attention, they're the ones carrying signals, not fluids. We're talking about fiber optic tie-ins, copper tie-in points, and especially DCS, that's Distributed Control System Redundant Connections over Modbus. So why signals? Well, if two pipes don't align, you can physically see it, right? But with a control system, you've got an A path and a B path. Both of those redundant paths have to be fully proven by both parties to the exact same protocol specification. It is absolutely not enough for them to just be plugged in or connected. If they aren't communicating perfectly, your safety and control systems are totally blind and you literally cannot start the facility. To really put this into perspective, let's look at the absolute biggest interface on a floating production project. And that's bridging the subsea production system, or SPS, to the vessel's hull and topsides. This is a massive gap. The equipment down on the seabed is often built by a totally different contractor, managed by a different engineering discipline, and honestly, usually fabricated on an entirely different continent than the vessel floating right above it. The bridge between that dark seabed and the bright, air-conditioned topsides control room happens at one very specific point: the data transfer junction box. And the source data makes one thing crystal clear here. The secret to surviving this is ruthlessly mapping every single signal crossing that box on both sides, way before anyone even thinks about cutting a single piece of steel. I love this next analogy because it brilliantly illustrates what happens when that mapping fails. Think of it as the two teams, one tunnel problem. Imagine you've got two crews building a tunnel from completely opposite sides of a mountain. Both crews dig brilliantly. They both hit their own internal survey marks absolutely perfectly. But when they finally break through the rock in the middle, they're offset by 2 meters. They completely miss each other. So how does that even happen when both teams did perfect work? Well, it happens because nobody owned the shared datum point from the very beginning. Both teams were quite literally referencing different maps. In the EPCI world, your shared datum isn't some survey stake hammered into the ground. Your shared datum is the signal exchange list at the battery limit. That's the master document. It dictates exactly how these systems are going to talk to each other. And here is the golden rule drawn straight from this analysis. That signal exchange list requires exactly one named owner on your org chart. Not a department, not a steering committee, and definitely not a generic team inbox. One named human being who is fully responsible for ensuring that contractor A's signals perfectly match contractor B's signals before a single piece of hardware is even ordered. I want to pause right here and ask you to really think about this scenario for a second. Let's say you've reached the commissioning phase. The modules are built, the facility is powering up, and boom, you find a signal list mismatch at that data transfer junction box we just talked about. What does that actually cost you? Most people instinctively look right at the procurement sheet. They think about the cost of buying a new circuit board or running a new cable, or maybe replacing the junction box itself. But as we're about to see, the hardware cost is basically just a rounding error compared to the real financial damage. Let's walk through the actual cost cascade. This is the brutal chain reaction of a battery limit failure. First, you've got field rework, and because you're already in the commissioning phase, you're doing this at offshore rates, which, as we know, are exponentially higher than onshore yard rates. Second, you suffer a complete commissioning freeze. You literally can't progress to the next system without this interface working, so all your highly paid commissioning teams are just sitting around idle. Third, because millions of dollars are now actively bleeding out, you enter a formal battery limit dispute between the two contractors over who is actually at fault, which burns endless legal and management hours. And finally, this delay pushes back your sail away date, triggering massive liquidated damages for late first oil. It's a total nightmare. And that whole nightmare scenario brings us to a fundamental law of project execution drawn right from the data. Interface failures are never, ever proportional to the size of the interface itself. That tiny little mismatch in the signal list, it didn't just cost you a few $1,000s in cables. The liquidated damages and the schedule overrun from this cascada are going to exceed the cost of the original hardware by 3 or 4 orders of magnitude. Listen closely to this part. You are paying a penalty measured in millions for a failure measured in millimeters. The physical size of that junction box has absolutely zero correlation with the sheer financial devastation it can cause if it fails. So, what do? How do we turn these insights into an actionable strategy? The analysis points to a really clear input-to-outcome roadmap. First, you've got to proactively identify all your battery limits, and you need to treat the data and signal interfaces with the exact same respect you'd give a heavy structural weld. Second, name a single specific owner for every single interface on the whole project. Third, absolutely insist that your signal exchange lists are fully agreed upon and totally frozen before anyone builds a thing. And finally, you have to lead your teams with the clear recognition that the cost of failure at the edges is never proportional to the size of the components. You came into this explainer understanding your own scope, but now you have the tools to actually manage the gaps. I want to leave you with this one final provocative thought. Take a look at your current projects. Really look at your organizational chart. And ask yourself, why does a $15,000 junction box deserve director-level attention? Well, because now you know that the box isn't just hardware. It's the bridge between millions of dollars of isolated brilliance. If you don't actively manage the dashed lines on your drawings, those dashed lines are eventually going to manage you. And trust me, they will charge you $1 million a day for the privilege. Thanks so much for joining me in this explainer, and I'll see you in the next one.